Hello, my name is Daniel, and I'm a professor at Musashi University. In today's presentation, we're going to look at some fundamental principles of how machines learn, and specifically, we're going to look at some iterative methods. Now, by way of introduction, I want to begin and ask you a very simple question. A square has an area of 25. What is its side length? Well, clearly the side length must be square root of a, and in this trivial example, you know the answer. The answer is 5, of course. But what if I ask you what is the side length of a square with an area of 29? And now it's a bit more difficult, but probably you would guess that the answer must be somewhere between 5 and 6. And in order to give me a precise answer, you might pull out your calculator, type in 29, and get the correct solution. But how does your calculator actually know this answer? Well, it turns out that even modern calculators are based on an algorithm which is very closely related to an ancient algorithm, which is called Heron's method for finding square roots. Heron of Alexandria was an ancient Greek mathematician, an engineer, an inventor, who lived in Alexandria in Egypt around the 1st century AD. And he described a method for finding the square root of a number. Basically, it goes like this. You start with an initial guess, and then you iteratively improve the guess until the solution is good enough. So let x be our initial guess of the square root of a. Then clearly we have the following identity. A equals x times a divided by x, which is of course square root of a times square root of a. Now, if our initial guess x is smaller than the square root of a, then clearly a over x has to be larger than the square root of a, and vice versa. So the basic idea is really, why don't we average x and a over x? That should be a better approximation of the square root of a. And that leads to this formula here. xi plus 1, so the next better approximation is just the average of xi and a divided by xi. Let's see how that works in practice. So let's go back to my introductory example where the area is 25. So let's pretend that we don't know that the answer is 5. Okay. So what is the square root of a? And let's say our initial guess is x0 equals 10. I know this is a terrible guess, but just bear with me. So here in this table, I entered the corresponding numbers. And you see, the first better approximation, 6.25, is already much closer to the correct solution. Next, we continue with this approximation, and then we arrive at 5.125. And we continue analogously, and you see after just 5 iterations, we are already very close to the correct solution. Here's actually the geometric interpretation of what we just did. So we started with a rectangle with the following side length. And then we iteratively changed the length while keeping the total area constant. Here's Heron's method defined a bit more formally. So let a be a real positive number. We choose a positive x0 as our initial guess of the square root of a. And then we define a sequence by the following formula. And this sequence is called Heron's method. It's also known by the name Babylonian method because actually the idea was already known in ancient Babylon many, many years before Heron. Anyway, this sequence converges to the square root of a. Now, in practical applications, the iteration is terminated when we are close enough to the solution. So when xi squared minus a, the absolute value of that, is smaller than or equal some small positive number epsilon, where epsilon is a prescribed error tolerance. Now, Heron's method illustrates a fundamental idea of how machines learn. We start with a guess, often called random initialization. We then improve the guess in an iterative process, and we stop when the result is good enough. So when we have achieved a sufficiently small error. In machine learning, a machine typically means an algorithm or a model. More precisely, machine learning is a branch of artificial intelligence that enables computers to learn from data and make decisions or predictions. So here's an example from my own research. So we used machine learning models to predict the outcomes of real future soccer matches. So for example, what is the probability that Team A will win against Team B? What makes machine learning so exciting is that it allows computers to learn from experience rather than just follow fixed instructions. That means that we can build systems that improve over time, like recognizing images, understanding language, or making predictions for real future events. In my own research, for example, I used machine learning to predict the outcomes of real future soccer matches. That was an immensely exciting project. But perhaps the real excitement even goes beyond technology. So applied machine learning is a highly interdisciplinary field of research with applications in many different domains. So for example, you can use machine learning to assist in diagnosing disease, to make transportation safer, or to create new forms of art and entertainment. That also means that you can collaborate with people from different backgrounds. So in my own research, for example, I've collaborated with medical doctors, biologists, chemists, and even football experts. Today's lecture is on iterative methods and unconstrained optimization. But before we come to optimization, we need to have a look at a different topic first. And that topic is called root finding. So here's a very simple example. What are the roots of the function f of x equals x squared minus 1? Well, this is a trivial example. You see here the graph of that function, and the graph of the function crosses the x-axis at minus 1 and plus 1, so the roots are minus 1 and plus 1. This is easy. Here in example 2, however, when I ask you what are the roots of half times x minus the natural log of x minus 3, well, this is actually quite difficult, and the reason is there are no elementary closed form solutions. Here in the graph we can see that there are clearly two roots. But how can we find them? Well, luckily there are approximations. And one of the most important methods is called the Newton-Raphson method. It's named after Isaac Newton and Joseph Raphson. It is an iterative method for finding the zeros of a function. The method begins with an initial guess or approximation of a root, and then this approximation is iteratively improved until no further improvements are required. Let's go back to my introductory example here. So here the simple graph. So where are the roots? I start here with a value of x0. And as you can see, this is a pretty bad guess. So we are quite far away from the root plus 1. And the first thing we do, well, we calculate the tangent line to the graph at that point x0. So here's the familiar formula of the tangent line. And we can see that this tangent line crosses the x-axis at a value x1, which is already much closer to the root. By the way, in my lecture, I will often say f prime of x. The same is, of course, f dash of x. So these two expressions are used interchangeably. Clearly, f prime of x or f dash of x, well, that is the slope of the tangent line. So f dash of at x0 is here the slope of the tangent line. Let's have a look now at the relationship between x1 and x0. So clearly x1 is x0 minus delta x. Please note that we have a right triangle here, so clearly we have the following expression. So f at x0 divided by delta x, well, this is just f dash x0 or f prime of x0. That's just the slope of the tangent line, right, by definition. Now, just by rearranging, we see here, we get the following expression for delta x. So, and the relation between x1 and x0 is clearly now given by this equation here. So x1 is x0 minus f of x0 divided by f dash x0. And now we do the same, but we start at x1. So, and then we calculate a new tangent line, and we see that new tangent line crosses the x-axis at x2. So x2 is our next better approximation. And we continue. So we have here an iterative method. xi plus 1 is xi minus f of xi divided by f dash xi. Here's the Newton-Raphson method defined a bit more formally. So let f be a continuously differentiable function. Let x0 be an initial approximation to a root. We suppose, of course, that f prime at xi is not 0. Otherwise, the whole method will not work. And then we define a sequence by the following equation. And this sequence, well, if the sequence converges, then it is a limit, when its limit is a root of f. And this iteration is known as the Newton-Raphson method. In practical applications, the iteration is terminated when we are close enough to a solution. So when the absolute value of f at xi is smaller than some prescribed error tolerance. By the way, Heron's method can be regarded as a special case of the Newton-Raphson method. So we can consider f of x equals x squared equals a. So of course the same as x squared minus a equals 0. And here on top we see the Newton-Raphson formula. And just by doing a little bit of algebra, you see here at the end we arrive at Heron's formula. Why does root finding actually matter? Well, approximating roots of functions plays a fundamental role in numerical methods, and it's also closely connected to optimization. So consider, for example, finding the local extrema of a function f of x. How would you do that? Well, you compute f prime of x or f dash of x. You solve by setting f prime of x to 0. You calculate this to find the critical points x0, and then you apply the second derivative test to find out whether you are dealing with a local maximum or a local minimum. And indeed, the central problem of optimization is the minimization or maximization of a function. Newton's method can also be used in optimization. Let f now be a twice differentiable function and we seek to locally minimize f. We suppose that f double dash, the second derivative, at xi is not zero whenever the iteration is defined. And when we define a sequence by the following formula here. So please note, this is essentially the same as the Newton-Raphson method, except that f has been replaced by f prime, and f prime has been replaced by f double prime or double dash, so the second derivative. And if the sequence converges, then its limit is a root of f prime. That means it's a stationary point of f, and that may correspond to a local minimum. In practical applications, the iteration is terminated, again when we are close enough to our goal. So here, when the absolute value of f prime at xi is smaller than or equal some prescribed error tolerance. Let's have a look at an example. So suppose we want to find a local minimum of the following function. So here's the graph of that function. We can clearly see this function has a local maximum. It also has a local minimum. And these points here are at -1 and +3. Okay, we can see the slope of the tangent lines here is of course 0. Here's the graph of the first derivative of that function. And here is Newton's formula in optimization. Okay, and here I just plugged in the corresponding values so for this function here. Let's suppose that we start at a random starting point x0 equals 6, okay? And our goal is here to find the local minimum at +3. Now, the method tells us that the next better approximation is x1, which is 3.9. So already pretty close to the correct solution. Next, x2 is 3.14, and the next one 3.0046, already pretty close to the correct solution. And we can continue analogously to get closer and closer to the local minimum, which is 3. There is, however, a small problem, so there is no guarantee that the method converges for arbitrary initial values. And indeed, the method may also move uphill and converge to a local maximum. That indeed would happen if we had started here somewhere between -3 and -4. If that had been our starting point, we would have landed in the local maximum at -1. There are some tricks, however, to make the method always move downhill, but that's a topic for another lecture. Machine learning is a very active field of research with many important and rapidly evolving topics. So one of the most visible ones at the moment is certainly generative AI. So these are models that can create text, images, videos, or computer code. And a major driver of this recent progress is the rise of large language models, such as GPT-4, which can understand and generate human-like language. And in essence, these models rely on architectures like the transformer, enabling them to capture complex patterns in language and to perform a wide range of tasks, so from communication to translation, to coding assistance, and even to something that resembles human-like logical reasoning. And as large language models continue to improve, they are becoming, of course, central to generative AI. But also raises some questions, of course, about their responsible use. Another important topic is the topic of interpretability, so specifically in sensible domains like healthcare and finance. We also want to understand how and why a model makes its predictions or decisions. Finally, another important and very interesting topic, which is also an area of my own research, is the topic of reproducibility. So sometimes small changes in training data can lead to different results. So making sure that computational experiments are reproducible is also a major challenge. In the last part of my presentation, I would like to talk about a very important algorithm in machine learning. It's called gradient descent. Gradient descent is an iterative method that minimizes a function by repeatedly moving in the direction of the steepest descent. So that's the direction of the negative gradient. Today's lecture will focus on the basic idea of gradient descent. But first, so that we are all on the same page, what is a slope? What is a gradient? Well, if a function f of x is differentiable at a point x0, then its first derivative at that point, denoted by f prime of x0, well, is equal to the slope of the tangent line to the graph of f at x0. This is indeed what we saw earlier in the Newton-Raphson method. In the single variable case, the slope plays the same role as the gradient in multivariable calculus. So typically we talk about a gradient when we have a multivariable function, such as f of x1, x2, and so on. Then the partial derivatives, they measure the rate of change with respect to each variable. And the gradient is just a vector of all partial derivatives and is denoted by nabla f of x. Let's have a look at an example. So our goal is to find the minimum of the following function, f of x equals x squared. But we want to find it numerically. Well, clearly the minimum is at x equals 0. Let's suppose that we start from a random point x0, for example, at -2 or +1. What can we say about the slope? Well, clearly here at -2, we see that we have a negative slope or negative gradient, if you like. And what does that mean? Well, the minimum is to the right of that point. So we should go to the right if we want to find the minimum. On the other hand, here at the point 1, we see a positive slope, and that means that we should go to the left, because the minimum is to the left. So gradient descent means taking a step in the direction of the negative gradient. Here's the basic gradient descent algorithm defined a bit more formally. So let f of x be a differentiable function, and f prime of x is its derivative. Let x0 be an initial guess of a local minimum. Then a better approximation is obtained by the following equation. So x1 is x0 minus, and this is called eta. So eta times f prime of x0. Now here eta is a small positive number, maybe 0.01, and it's called the step size. And in machine learning, it's also often called the learning rate. And this update is applied iteratively. So we have the following update formula. Now, importantly, at each step, the method moves in the direction of the steepest descent. And when do we stop? Yeah, we stop maybe after a fixed number of steps, or when we're close enough to a solution. So when the absolute value of f prime at xi is smaller than some acceptable error. Typically, however, we use gradient descent in higher dimensions. So let f, now x is a differentiable function. Now, f of x is a differentiable function, but x is here a vector. And nabla f of x denotes the gradient vector. Okay. Now, starting from an initial x0, the gradient descent update rule is given by this formula here. Okay, right? But in essence, it's the same as in one dimension, except that here we have the gradient. Again, importantly, at each step, the method moves in the direction of the steepest descent, which is given by the negative gradient. And this process is repeated until a stopping condition is met, such as a prescribed number of iterations has been reached, or again when we are close enough. Well, here close enough to a stationary point, so when the gradient norm becomes sufficiently small. Let's have a look at an example. So let's find the minima of the following function, and perhaps at first sight this function looks a bit harmless, but it's actually quite difficult. We can see here this function has clearly, it has a global minimum here somewhere between -1 and -2. And it has a local minimum somewhere between +1 and +2. And let's remember, why do we want to find the minimum again of a function? Well, this is a very common question. You could imagine like a cost function, and you could ask for which x are the costs minimal. Right? This might be a question in economics, for example. Now here we see that we have the global minimum at -1.444, and we see that we have the local minimum at 1.382. Let's suppose that we start at a random starting point here, x0 equals 2. Now, the image I would like you to keep in mind is that of a small ball that is rolling downhill. So this ball would roll downhill and land here in a valley. So it would land in the local minimum. Or if we let a ball roll downhill from here, it would also land in the local minimum. But on the other hand, if we let the ball roll downhill from around here, the ball would land in the global minimum. Let's see how it actually works. So here I implemented gradient descent for this particular function in R. I begin with my initial guess of the minimum, which is x equals 2. Here's my learning rate, eta, 0.01. Actually, finding the right eta is not trivial. If it's too large, the method may overshoot the minimum. And if it's too small, convergence is slow. Here's my acceptable error, epsilon, a very small positive number. My maximum number of iterations, 1000. Here's the first derivative of the function. And here I implement gradient descent in a while loop. So while the absolute value of the first derivative is still larger than epsilon, and we haven't reached the maximum number of iterations yet, we apply the update rule. So this R code here corresponds to this formula here. And we can see that after 82 steps, we found the approximated minimum, here this value 1.3818 and so on. It's exactly this value here. But let's keep in mind, the result here depends on the start point. If our initial guess had been x minus 2, well, we would have landed here in the global minimum, right? After 71 steps, the approximated minimum is minus 1.44 and so on. Indeed, any starting point from here would lead to the global minimum. This example also shows a limitation of gradient descent. So gradient descent may converge to a local minimum. It does not guarantee a global minimum. Also, finding the right step size eta can be difficult. So if it's too large, then gradient descent may not converge. And on the other hand, if it's too small, gradient descent may be too slow. This problem can be addressed by using more advanced methods. So, for example, by using a variable eta. So we have eta I. Also, gradient descent fails for non-differentiable functions. Gradient descent is a very popular algorithm for training neural networks, or to be more precise, a particular type of neural networks, which are called feed-forward multilayer perceptrons. Actually, the goal during training is to minimize an error function, also often called a cost function. This error depends on the network's parameters, which are known as weights. How do humans actually learn? For example, how do we learn how to recognize images or symbols? Well, obviously we use our brain, which contains a sophisticated network of interconnected neurons, which basically, for example, allow us to recognize that this here is the kanji for cat. In the year 1943, the first mathematical model of an artificial neuron was developed, which led to more research on artificial neural networks and later to something called multi-layered architectures. But I believe we are getting a bit ahead of ourselves, so let's keep things simple for now. So I want you to think about a neural network, or indeed any machine learning model for now. Just think of it like a black box. Okay, it's a black box with some parameters, some internal mechanism, some internal algorithm. And these parameters here, theta, let's call them theta. Theta here is a vector, so we have theta 1, theta 2, and so on. What is a model in essence? So a model in essence is something that takes some input, then does something with that input and produces some output. You could imagine the black box like a black box with some knobs here that you can tweak, and depending on these different parameter settings, you produce a different result. Now, the produced result may not be what you hoped to get, so the produced output is not the desired output. So, for example, for this particular input here, the output dog would not be correct. But the good thing is that we can define an error function based on the discrepancy between produced and desired output. And then we can iteratively update theta to minimize the error function. Now, suppose that we have only two parameters called theta 1 and theta 2. Well, the error function is then dependent only on theta 1 and theta 2, and we can visualize the error function as an error surface, right? It looks like a rugged landscape with hills, plateaus, some valleys. And ideally we would like to find that combination of theta 1 and theta 2 for which we can reach the deepest valley. This is where the error function has its global minimum. Here on the right-hand side, we see essentially the same information just represented as a contour plot. Now, we have to keep in mind the following. Gradient descent moves in the direction of the steepest descent. But the gradient only reflects local information about the error function. We do not have access to the entire error surface. So as an analogy, you could imagine that you are hiking in the dark. So we are on top of a mountain, for example, and we are trying to find our way to a valley, but we can only see like one step ahead, and we go in the direction of the steepest descent. In real artificial neural networks, there are of course many parameters, sometimes millions of them, and of course the error surface is then really high dimensional and we cannot visualize it anymore. Okay, and this brings me to the end of my presentation today. So today we looked at first a very ancient algorithm called Heron's method for finding the square root. Then we looked at the Newton-Raphson method, first for root finding, then for optimization, and then finally we looked at a very important machine learning algorithm, which is called gradient descent. Iterative methods are really fundamental to machine learning. Many problems reduce to minimizing an error function. And in machine learning, so specifically supervised machine learning, this often defines the learning process. Okay, thank you very much. The future of machine learning is certainly promising, but it also comes with important challenges. So we likely see it used more widely in areas like healthcare, finance, but also education. But that does not automatically mean that everything will automatically improve. So systems can make mistakes, behave sometimes unpredictably, or rely on patterns that aren't fully understood. Because of that, a big part of the future of the research in this field will not just be about building more powerful models, but also making sure that the predictions and decisions are interpretable so that the results can be trusted. In terms of education, I believe that the fundamental topics, like the ones that I presented in my lecture today, will remain highly relevant and will of course also be included in future curricula.